Hello, and welcome to this session on scaling Redpanda. My name's John Spray, and I'm with the core engineering team here at Redpanda. I'm based in the UK, in semi-rural Hampshire. My background prior to joining Redpanda is primarily in distributed storage systems, a couple of file systems you might have heard of. And I spend my days focusing on scale, robustness, and correctness in our system. So why would we want to scale Redpanda? Why is a bigger system useful? The main axis of scale that I'm going to talk about is partition count. Partitions are the unit of work for Kafka applications. It's how work gets spread out between large numbers of consumers. So if you want to share your data between 10,000 consumers, you might need 10,000 partitions. Not every application has that scale need, but the improvements we make to support scale also improve efficiency for all other users. So imagine densifying a system, whether we're adding cores to get higher overall scale or increasing density to get a cheaper system at smaller scale. Broadly, the same changes to the software apply. Before I go into detail, a little refresh on the architecture of Redpanda. So each partition in Redpanda is a raft group. Raft is the consensus protocol that we use to consistently replicate the data across groups of nodes, usually 3 nodes. Each of those partitions also has some memory and resource footprint associated with the files that it has on disk. And client connections to a Redpanda cluster also come with some resource overhead from their TCP connections. The underlying storage for a partition is log structured, which makes it very fast for writes, but imposes some costs when we need to do replay at startup. So to get an idea of the types of resource quantity we're talking about, imagine 1,000 partitions per core, which is sort of at the upper end of what I test in my work, and a gigabyte of RAM per core. That leaves only a megabyte of memory for each partition. So the question is, how do we do a good job within that narrow resource footprint? So recently we've made some improvements to Redpanda aimed at solving these problems and enabling high-scale systems. I'm going to talk about storage first because that's kind of the bottom of the stack. On startup, we replay data from every partition. We have to replay from the last time that we took a snapshot of our internal state. That state is things like what transactions are going on, where we're at with uploading to tiered storage, and various other housekeeping. We used to do snapshots at a fixed interval, but that creates a problem when you have a large number of partitions because it just adds up to a lot of dirty data and leads to a long startup time. So now there's a setting, storage target replay bytes, that lets you say essentially how long you want Redpanda to take to start up. The default is 10 gigabytes, which on a typical system is about 10 seconds. You can increase that for less frequent snapshots or decrease it for faster startup. It's up to you. But the startup time no longer increases as you add more partitions. Partitions also reserve some disk space before they start writing. Similarly, this used to be a fixed amount per partition, and now it's dynamically adjusted across all the partitions on a node in response to disk space pressure. So you can't fill up your disk anymore. Even if you create a lot of partitions, at least you can't fill it up from the reservations. You can, of course, still fill it up by writing a lot of data in. Moving up from the storage stack, as we hit the raft layer and the Kafka layer, there are a number of so-called thundering herd problems. These are any event that's likely to correlate in time across a large number of entities, be those clients or partitions. So when clients do a metadata refresh in the Kafka protocol, they're likely to all do it at the same time because they're all responding to some change on the server side, such as movement of leadership. What's worse is that the size of a metadata response grows with the number of partitions in the system. So if you're scaling client count and partition count linearly with each other, it becomes an n-squared overhead that we have to do our best to deal with. Raft recovery and elections are also events that tend to come in a thundering herd when a node restarts and all the partitions on that node need some attention. So we've mitigated this in a variety of ways. The client metadata requests are now more intelligently throttled based on the anticipated memory use of the request. We used to just do this based on the request size. Now we estimate how large the response would be and use that to determine how many metadata requests we should try and process at the same time. We also induce fewer metadata requests by moving leaderships in a larger batch. So rather than trickling in leadership movements as we balance work across the cluster, we batch them up into larger movements, and that reduces the total number of metadata requests. When it comes to the raft layer, we introduce per core budgets for how many of these operations we'll do in parallel. And that implicitly limits the number of concurrent IOs, which implicitly limits the peak memory usage. For recovery, we can even go a little better. There's a feature called coordinated recovery, which is currently in a pull request, that looks at the overall queue of partitions that need to recover and prioritizes them. Small partitions get recovered first. Internal partitions get recovered first, rather than a situation where every partition tries to recover at the same time and contends for resources in a way that's unnecessary. So given those improvements that are internal to Redpanda, I can talk a little bit about how you put them into the field and how you size and manage a system at scale. Your first question might be, scale up or scale out? Should I have a lot of small nodes or a few big nodes? In general, you should lean towards scaling up. Redpanda is very efficient at using systems with a lot of cores. The C* framework that Redpanda is based on provides good isolation of memory between cores, and we get more or less linear scaling as you add cores to a system. Big nodes are also helpful for dealing with the Kafka protocol, which tends to cause all clients to open a connection to all nodes. Because the clients are talking to all of the nodes, adding nodes doesn't spread out the overhead of client connections. You just have more connections. So that is another reason why bigger nodes are generally better than more nodes. The flip side to this is that you do want enough nodes that having one of them down is a manageable small percentage of your system. If one node in a 3-node cluster goes down, that's 33% of the cluster offline. That's a lot. That means you probably had to over-provision the cluster by 30% to be ready for that. The higher the number of nodes, the smaller the percentage when one node goes down. So it's a balance between these two factors. In general, we're improving the software to dynamically adjust things like buffer sizes and things like how we allocate memory, so that you don't need to think too much about tuning. At the moment, there are still a few things it's worth knowing about if you're deploying at high scale, especially the storage read buffer size and the Kafka RPC server TCP buffer sizes. These default to 128 kilobytes in the case of storage read buffer, and up to megabytes in the case of TCP buffers. If our default is to let the kernel handle it, and the kernel will sometimes grow your buffers that big. So if you remember that 1 megabyte partition number at very high density, we need to think about these numbers in that context. You probably don't want to use 10% of your partition's memory for one read buffer. So you can tune these numbers down. Something like 32 kilobytes for a read buffer doesn't give you such good streaming throughput for one partition, but it's a good defensive measure to take if your goal is to multiplex the I/O from very many partitions on one machine. Finally, if you have deployed a system like this and you want to validate your configuration, you want to validate your hardware, there are some things you should do beyond starting it up and running a typical benchmark. Write a lot of data. Try and fill up your disks, or at least half fill your disks, so that you're accounting for the memory overhead of tracking all of those segments. Stress test the system with rolling restarts of nodes. Restarts are one of the most stressful times for the system because it's trying to recover data from all partitions at the same time. Run it with a node out so that you can size the system to work well, even in the middle of maintenance. And other lifecycle operations like adding and removing nodes are worth testing at scale, since they're likely to touch a large number of partitions at the same time. And really, none of these tips are specific to Redpanda. It's a good idea for any distributed system. Thank you very much for joining. My contact details are on this slide. Thank you.